of Yashar. It's gonna have the title Shedding Light on Dark Matter, How with Artificial Intelligence and Cosmic Lenses. Thanks for being here. And so the way this panel is gonna work is that each speaker is gonna give a 20-minute talk, and then we have 40 minutes for a Q&A session. Thanks. And yeah, I invite now Katelin here. I think, yeah, you need to, maybe I'm not good with microphones, but yeah, you need to.
Can you guys all hear me?
Yes.
Excellent. Good. Okay, so as Valentina alluded to, my name is Katelin Schutz. I'm a professor here. I'm in the Canada Research Chair in Astrophysics Beyond the Standard Model. And today I'm very excited to tell you about exactly how it is that we can look for this invisible substance known as dark matter and precisely how it shapes our universe in ways that we can measure. So now, right off the bat, I want to dispel a common stereotype when it comes to dark matter. People maybe think about the dark side of the force or, science fiction, more broadly speaking. But really want to quickly dispel that notion and really to emphasize that we are not talking about something from science fiction today, but rather we are living in this era where we have a really vast wealth of different data sets that are telling us all kinds of unique pieces of information about the presence of dark matter. And here are just a couple of examples from recent years of different kinds of data sets that tell us about dark matter. So I'll be touching on some of these today during my talk. But I want to be very clear about defining my terms. Okay, so the title of my talk alludes to things that are invisible. And if you look up the dictionary definition of the word invisible, it's incapable by nature of being seen. Okay, that's the Merriam-Webster definition. I want to use a slightly more specific definition for the purposes of my talk, which is fundamentally transparent and not interacting very much with light. Because after all, light is the modality by which we visually see things, right? That's how I can see you in this room. And actually, when it comes down to it, most of the sensors that we've developed over, mankind and the evolution of technology, those sensors all deal with interactions with light at some fundamental level, okay? So I'm going to be telling you about something which does not interact very much with light. And so therefore, it has been very, very elusive to try to find it with our detectors, which again, are based primarily on detecting light. So at the end of this talk, so my goal is to convince you that just because something doesn't interact with light doesn't mean that we can't discover it, and that dark matter has many observable consequences. We may not be able to reach out and touch it, okay, but we can still infer what kind of consequences it's going to have. So that's the goal of my presentation today. And I want to start kind of by recapping what we already know about the contents of our universe. So the 4 known forces that we already have at least a pretty good handle on, both theoretically and experimentally, okay? So I want to start with the strong nuclear force, okay? And the strong force is felt by these particles that are called quarks, okay? We've got all these different flavors of quarks, and they have funny names like up and down, charm and strange, top and bottom. But if this sounds exotic to you, it may be more familiar to learn that this is actually what protons and neutrons are made of. Okay, so the strong nuclear force is what holds quarks together to form protons and neutrons, which you may have learned about in a chemistry class. That forms the kind of central core of an atomic nucleus. So these are the building blocks of atoms. All right, so that's the strong force. I like to kind of think of it as a Venn diagram. So now I'm going to talk about electromagnetism. Okay, that's kind of the next strongest force that we know about. And all of these quarks that I've shown you here are charged. Okay, so they all are charged under electromagnetism, which means that they talk to the electromagnetic force. And so in addition to these nice quarks that we already have here, we also have particles that are called leptons, and these are the charged leptons. Okay, for example, the most familiar example is probably the electron, okay, again, which is an important component of the atom. And interactions with the electron are responsible for giving us chemistry, okay? But maybe more exotic, less familiar, the electron also has heavier cousins called muon and tau, okay? They're just like the electron in that they are charged, negatively charged, but they're just a little bit heavier, all right? Moving on with our tour of the four forces, the next weakest force is appropriately known as the weak force, the weak nuclear force. Clearly physicists were not very good at branding, okay? And all of the particles I've mentioned already all interact via the weak force. Oftentimes, the weak force is so weak that it's not really very relevant. However, in addition to the particles that I've already told you about, we also have this new class of neutral leptons, which are called neutrinos, which implies that they're neutral. And ino, I guess that's an ending in Italian or other Romance languages, that means it's little. And we're going to come back to neutrinos later on in this talk. And of course, the force that we're most familiar with, as small children learning how to walk, is the force of gravity, okay? It's a very weak force, but nevertheless, the Earth is massive enough that gravity is an important force which keeps us bound to Earth. And one really amazing thing about gravity is that it's actually universal. So anything that has mass or energy is going to experience the gravitational force. And so that's why it is the outermost bubble on this Venn diagram. And the fact that it has to be the outermost bubble on the Venn diagram, the fact that anything that has mass or energy is going to gravitate, that amazing fact is precisely what has allowed us to infer the presence of a new type of particle. And I'm going to show you all of the evidence, well, maybe not all of the evidence, but I'm going to give you a little tour of a good cross-section of the evidence as to why we think these particles are there. However, at this point in time, I think hopefully it's maybe not too implausible that we see this very rich structure over here going on with the standard model. We have four forces, we have all these different kinds of particles. Some of these particles are very exotic to us because there aren't very many of them around, okay? So they're not very abundant in our universe, okay? So we have all this extra stuff, basically, in the standard model. It's very complicated. And this kind of flies in the face of something known as Occam's razor, which says that things should be simple. Okay, clearly this is not simple. And actually beyond this Venn diagram, there's all kinds of other reasons why the known particles are not simple. Okay, so hopefully it's not too implausible to imagine like any new kind of particle that we discover, it may come along, for example, with its own bubble of the Venn diagram. Maybe that bubble overlaps a little bit with some of the particles that we know about. So maybe there's some crossover, or perhaps more pessimistically, maybe that new kind of bubble of the Venn diagram is kind of separated, it doesn't interact. However, again, at the very, very minimum, gravity is at the outermost layer of this Venn diagram. And so at the very minimum, gravity can tell us something about what's going on inside of that orange bubble on the Venn diagram, because that orange bubble is going to interact with us via gravity. So for the remainder of my talk, I'm going to tell you a bunch of gravitational pieces of evidence for the existence of dark matter. And I'm going to be focusing on a wide variety of astrophysical systems, kind of doing a flash tour. And they span a huge range of, different physical length scales. So 9 orders of magnitude in length, also a huge range of time scales. So from the earliest moments of the universe to the present day, okay? And in this talk, I'm going to try to emphasize that we're not just kind of cooking up some weird theories, and sitting and stroking our proverbial beards, in the library, right? We're really doing this in a way that's empirically driven and thinking about the properties of dark matter in a way that is consistent with observation, okay? So with that, I want to first tell you about some very local pieces of evidence for dark matter in our sort of nearby region of outer space. And I want to tell you a little bit about this woman right here, Vera Rubin, who did some really important work on this topic back in the 70s and 80s. And she made a very important discovery, which was as follows. So here on the y-axis of this graph, I'm showing the speed of how quickly things rotate around in a galaxy, okay? On the x-axis, I'm showing how far are we away from the center of that galaxy, okay? So as you may know, here on Earth, right, our gravity is quite strong, right? It's strong enough that it's keeping us bound to the Earth. But as we go further and further away from Earth, like if we were going on a rocket into space, we would feel relatively weightless because the gravity would be much less. Okay, so that difference, we would also expect to see the same thing occurring here as you go further and further away from the center of a galaxy. Okay, but that's not really what we see. So the effects of gravity don't really seem to be getting weaker. So this velocity going down is telling you that your gravitational field is diminishing at larger and larger radii, because you don't need to have as much gravitational force to pull things in that are spinning around like this. All right. So instead, what Vera Rubin and her collaborators observed is that actually, as you move further and further away from the center of a galaxy, it's actually the speed is constant or even in some cases increasing. And in order for this galaxy and on all of these outer reaches to not just completely fly apart, we need some additional gravity holding everything in together, okay? And that gravity that needs to be there to hold things in, it cannot be accounted for by the visible matter that we see. Okay, we see actually, the visible matter, it's kind of quite bright and then it's dying off pretty quickly. And yet out here, far, far away from the galaxy, there still seems to be mass that has to be there in order to account for this. And we don't just see this in one galaxy. This is ubiquitous when we look at many, many different galaxies. So going to other galaxies, so galaxies are not all like the Milky Way. There's actually a really big diversity of different kinds of galaxies, because the components of galaxies are such that you can mix and match the different ingredients. So just like in baking, maybe you mix the ingredients one way and you get a cookie, other times you get a cake. The same is true in galaxies. All right, so here's one example of a kind of funny galaxy. This galaxy is called Eridanus 2. And as you can see, it's super, super faint. So if I didn't tell you there was a galaxy in that picture, you might not be able to see it. You see there's a very, very dim kind of faint overdensity of stars, okay? But it's the kind of thing where, if you weren't specifically looking for it, you could easily miss that. However, when we measure the speeds of these stars and we try to infer how much matter is there, counting for, holding them in together, we come up with a number where we find that actually most of the mass in this picture is actually dark matter, 99.7% of the mass. This is a very dark matter dominated system. We have a lot more dark matter than regular matter. In contrast, we actually have other examples of very diffuse galaxies that have almost no dark matter in them at all. So that's the other extreme. This is an image taken with the Dragonfly photo array. And this galaxy right here, it is actually spatially as large as the Milky Way, but it's just like 1,000 times less massive than the Milky Way because it's very deficient in dark matter, okay? So the fact that we're able to not only have to have extra mass to explain these observations, but also that it seems like you need adding mass in different amounts in different environments. That's kind of telling you, okay, maybe, it's not just that we don't understand gravity, but it really seems like this is an ingredient. This is a component that can vary in its amount in different places. It's not just a rescaling of gravity. That evidence is further strengthened when we go to clusters of galaxies, which, as the name implies, is just a cluster of galaxies. And here's the most famous example, where you have two galaxy clusters that have merged, and we are looking at the aftermath. It's kind of like, being a crash inspector, right? Trying to figure out the aftermaths of what happened. And here's what we see when we look at this composite image. On the one hand, we have the Chandra X-ray Space Telescope, which has been taking images of galaxy clusters for the past several decades. And it's able to infer where where X-rays are being emitted. It's an X-ray telescope. And that is what we see in these pink regions, okay? That is basically normal matter, which is really hot, and so it's emitting a lot of X-rays. At the same time, in this image, we can see, using a technique called gravitational lensing, where this matter is bending the light, okay? We can use that effect to infer where most of the matter is in this picture. So coming back to this, okay? So Einstein tells us that matter bends space and time. It's deflecting light similar to how a lens is bending light in, glasses. And you can end up with all kinds of beautiful images. You're going to see more in Yashar's talk, but here's some examples. This is an extreme, strongly lensed system. And there's tons of examples of these that I'm sure you'll see. This is a fun one because the universe is like smiling at us, okay? But using these kinds of observations, you can actually tell, what was the properties of that lens that had to have led to this image being so warped, okay? Just like how, depending on what kind of corrective lens you need for your vision, they know exactly how to shape the glass in your glasses, okay? So we can figure out what kind of bending of space-time was necessary to produce the image, and the regions in blue are where we think the lenses have to be, okay? So just to kind of contextualize this image and why this is such good evidence for dark matter, here's kind of a cartoon or an artist depiction of what the collision would have looked like. Okay, so before the collision, here are the two galaxy clusters. The stuff in blue is, again, the stuff that represents the mass of the system. And the stuff in pink is what represents the normal visible matter, which is emitting X-rays. So it's hot. So as the merger is happening, okay, so the two galaxy clusters are passing through each other, you start to see this separation between the pink and the blue. And they get more and more separated as time goes on. And ultimately, you end up with this spatial separation between the pink, which again is the normal matter, and the blue, which is where the mass of the system is. That spatial separation is due to the fact that regular matter can collide with itself, right? So when I'm speaking to you right now, right, it's because there's like viscosity in the air. My vocal cords are able to push on the air molecules in this room and create a sustained sound wave, right? So that's a necessary component for a lot of the phenomena that we experience here on Earth, and it's true also in outer space. There's viscosity, there's a drag force. And that drag force is slowing down the pink stuff. But whatever was happening with the blue stuff, it was not experiencing that same level of drag. So it's not experiencing a viscosity. And that means that this blue stuff is not behaving like regular matter. It's not scattering on an interparticle by particle level. Okay, so that's behaving very, very differently than the matter that we know about. I want to end by telling you about some pieces of evidence for dark matter on the largest scales in the universe. Okay. So to do that, I want to maybe take a step back and note this really amazing fact, which is that when I'm looking at you, I'm actually not looking at you how you look right now. I'm looking at you like back in time, okay? Because light travels about 1 foot per nanosecond. So for the people in the front row, maybe I'm seeing how you looked 10 nanoseconds ago. Okay. So that's maybe not so impressive, but okay, if we start talking about astronomical distances, things that are many light years away, then it's taking years and years for that light to reach us. And you just keep repeating that argument to farther and farther distances. Eventually you start seeing light from billions of years ago, okay? So that's what we see when we look back in time. We see light from long, long time ago. And when the universe was younger, so when that light was emitted, it was also hotter, it was denser, the universe was smaller. And so eventually, if you take a bunch of stuff and you try to compress it, you get a phase transition. You go from having something like a gas to having something like what's called a plasma, okay? And in this plasma, you have all these free electrons, and light likes to scatter a lot on free electrons. So this plasma is actually opaque. We cannot see inside of it, just like how we can't see inside of a cloud. Okay? It's very opaque to light. So why am I telling you this? Well, because we've actually detected this plasma, and it's called the cosmic microwave background. Okay, so this cosmic microwave background is basically, telling us when we went from having a young universe that was opaque to light was scattering in it all the time. All the while the universe is expanding, it's cooling down, boom, phase transition happens. Suddenly it's cool enough, you can form atoms, and then the light can come to our telescope. So now the universe goes from being opaque to transparent, and we can actually see this thing. And this is what it looks like. It's so beautiful. It's a very difficult measurement, but we've been measuring it for some decades now. And we can really study in detail its properties. And in particular, we can make maps of it, or we can study, are these ripples random, or is there some kind of correlated structure to it? And indeed, there is a lot of structure shown here. What you're actually seeing here are sound waves, okay? Because in the early universe, if we have a bunch of matter, it's going to try to come together under the force of gravity, okay? So gravity's trying to pull everything together. We know this from experience. It's attractive. But at the same time, okay, the regular matter, it's interacting in this plasma. The electrons and the photons are scattering on each other all the time. And so at some level, the radiation pressure is trying to oppose the contraction. So you have gravity bringing things in, but radiation pressure is trying to push things away. And those are basically the two ingredients that you need to sustain a sound wave. You have compression and you have rarefaction. And so that's happening in our universe. Okay, so the regular matter is experiencing these two competing effects. However, the dark matter doesn't really care about radiation pressure. As we've established, it's not interacting with light. And so all it feels is gravity. And we can actually tell that it's there. We can see that it's there because when you put all that dark matter down there, it's going to weigh down these baryons. It's going to load them down. And in the tug of war between gravity and radiation pressure for the regular matter is going to see more gravity because of the presence of that dark matter there. And so that's going to have an imprint on how the sound waves look. By contrast, if your dark matter is interacting a little bit with this plasma in the early universe, now there's not as much dark matter that's down there, and it's going to tip the scales away from gravity. Okay, so now there's less gravity weighing down the regular matter. And this actually really matters. It's something we can measure. Here's an example from my recent work where we looked for the effects of this, and we could actually set the tightest constraints on the possibility of dark matter interacting with this plasma. Okay, so it's measurably different when you compare it to the beautiful data that we have from the cosmic microwave background. And that's not all, because these sound waves, we see the ripples of these sound waves in the early universe. These sound waves actually provide the initial conditions that allowed for matter to kind of come together and cluster and form galaxies. So the fact that we're even here is actually as a result of these sound waves. So here, what I'm showing you is an observation and a simulation where in the simulation, the initial conditions had these sound waves baked into them. And the two maps, they don't look identical, but statistically, we can actually compare at the statistical level. Could these maps have been drawn from the same distribution? And the answer is yes. Okay. So not only in the CMB, but also the fact that we are here. Now, in the last couple of minutes, I want to just tell you about a case study, the case study of the neutrino. I promised I would come back to that. And the neutrino is this really interesting particle because it was actually proposed because there seemed to be this weird observation that some of these radioactive processes did not seem to be preserving momentum. Okay, we seem to be losing some momentum in these processes. And Enrico Fermi is the one who said, well, maybe there's another particle there that allows you to conserve energy and momentum in these interactions. And he said, I've done a terrible thing. I have postulated a particle that cannot be detected. And indeed, it was very hard to detect this particle. But several decades after predicting the existence of these particles, again, to be consistent with the physical laws that we know about, we were finally able to detect neutrinos. And so Pauli sent them a case of French champagne. So coming back to this picture, so you'll notice that by my definition of dark, neutrinos are dark because they don't interact with light. They only interact with the weak force. And so initially, and for good reasons, people thought, well, maybe these could be the dark matter. Maybe this could be responsible for solving this issue. But that's not the case. So for example, in these two simulations, on the left, I'm showing neutrinos just being only 20% of the dark matter. So not even the whole thing. And comparing that on the right with what's known as cold dark matter, okay? So you can see even with neutrinos as 20% of the dark matter, it's visually obvious that these two maps are not statistically the same. Okay, the one on the left, you know, it's like more smeared out. The one on the right has this dark red spot. which is absent in the one on the left, right? So it's like, you know, this one has much more extreme contrast than the other one. And the reason for that is because neutrinos move very fast. So in the hot early universe, right, they have a hot temperature and they're very, very small, very light particles. So they're just zipping around and they don't like to gravitationally cluster, right? They're going way too fast, and little galaxies that are trying to form, they don't have enough staying power. They're not able to pull these neutrinos in because they're just going way too fast. And so that's why you see this difference, this obvious visual difference in the two maps. So the upshot of this, what we learned from this, is that dark matter really does have to be a new type of particle, a new type of matter. We see evidence for it across a vast range of scales. There's even more pieces of evidence that I haven't told you about, but I just tried to highlight the huge range of observables, each of which on its own, maybe you would think, oh, that's a little bit weird, but maybe there's something that can explain it. But it's really hard to come up with some way of explaining all of these observations at the same time if we don't have any dark matter. And I think we should be really optimistic because of the case study with neutrinos. Sometimes it's just hard, you don't discover it the next day. Sometimes you have to try really hard. So we're going to hear about some efforts to do that in the next talk. But with that, I'd just like to summarize and say that we can be very confident and infer that there's this stuff there, okay, it interacts with gravity. We're trying to figure out if it interacts any other way, so that's still pending. But we know for sure it's not regular matter. And what we'd like to do is understand, you know, in the context of the particles that we do know about already, is this kind of like its own bubble of that Venn diagram, or is it something more complex, okay? And one thing I hope I've highlighted through this talk is it's a really big universe. So there's all these different systems that you can kind of use as laboratories to figure out what the particles are in our universe. And that means there's a lot of room for creativity. So we really need all hands on deck. Thank you.
Yes, now we'll think about Katelin. Now we're gonna have the you might want to switch the microphone. Because or no, it's not very good. It's not that. It's bad. So I'm not.
We heard you very well. So
You have a loud voice.
you have a very good voice.
Hopefully not too loud. I got my neighbor there in the audience.
Do I join with audio or not?
You just
Probably not. That's
probably not.
getting the
Yeah,
audio
I am.
from there.
Yeah, I have to. You have your audio off, right, Katelin? Yeah. So okay, perfect. Yeah. So it's
Okay, so just screen sharing that.
just screen share. Yeah. Just gonna confirm that. Is it one?
Yeah, and okay. Trying not to tell myself like this. Good evening, everybody. Thank you for coming here. I would like to thank the organizers for organizing this event and for inviting me. That was a great talk by Katelin. So I'm just gonna kind of like, there was a lot of like interesting overlap and we're gonna keep on going. So I'll kind of start by saying that I think we'll try to get rid of the Zoom thing here. So in Katelin's talk, we saw plenty of observational evidence for the existence of dark matter on many different scales, from kind of like cosmic scales. He showed us that, you know, the cosmic microwave background to kind of like, you know, weaklings in the distortion in the light from, you know, hundreds, you know, thousands of galaxies. to clusters of galaxies and how then they bend the light, or individual galaxies and how stars rotate really fast around the galaxies, and that's how we know what the existence of dark matter. So, but dark matter is really invisible, right? So when we look at the sky, we don't see dark matter. What we see is the stars. We see the galaxies. We see the stars and galaxies. If you look at a tiny, tiny, tiny patch of sky, we'll see something like this, where every dot here is a galaxy. And every galaxy could have hundreds, of billions of stars in it. So every dot is a galaxy, and that's the stars that we see: regular matter, helium, hydrogen. That's what we see. But if we could see the dark matter underlying all of this, we would see these oceans and rivers of dark matter going through our universe. That is really the backbone, the skeleton of our universe. That, with this gravity, it's shaping the universe as we see it. So one way that we can study dark matter is using numerical simulations. I mean, it's computer simulations, computer models. And so think about these computer models as digital twins of our universe. What we do is that we distribute matter that we think is dark matter according to kind of like what we know about the early universe right after the Big Bang. And then we just let gravity do its job. And so after thousands and after billions of years, this dark matter starts to clustering and clumping together to form these structures that we see. And we call these dark matter halos. So everything that you see in this numerical simulation is a clump of dark matter, and we call it dark matter halos. So we can run these simulations. But what about galaxies and stars? So this is another simulation, and what you see here in dark, in black, is the dark matter. But what about stars and galaxies? And we have a theory for the formation of galaxies in this dark matter universe too. And so this is called our galaxy formation theory. And the idea here is that stars and galaxies, they form at the heart of these dark matter halos. So a dark matter halo with all its gravity, it pulls the regular matter, the hydrogen, the helium, to its kind of core center, and we get these galaxies in there. And so smaller dark matter halos, they form smaller galaxies. Bigger dark matter halos, they form bigger galaxies. And this is really amazing. It's a little bit like image of a light bulb. So if you have a light bulb, you have this shiny filament of regular matter, the stars in the galaxy, embedded in this glass bulb, invisible glass bulb of dark matter. That's the way to think about this. So everywhere that we look at these sort of dark matter halos in our simulations, in numerical simulations, we can kind of paint a galaxy in there. For bigger halos, we can put bigger galaxies. For smaller halos, we can put smaller galaxies. And this is a really powerful prediction, because now we can go and compare this with our observations of the actual galaxies in the universe. And that is really amazing, because we find almost perfect agreement between the distribution of matter predicted by these dark matter simulations and what we get out of our observations of the real universe. So here you see this black curve that is basically a statistical measure of how these distribution of matters, they match. So that's great, but there are a few little problems here. So here's, again, you're looking at one of these simulations. We're looking at very, very large scales in our universe. And you can see all these dark matter halos that are the places where galaxies they form. And if you zoom in on this, we can just zoom in on this simulation. That's 1 gigaparsec, so 1 billion light years, or some fraction of 3 times light years. And then we can zoom in more and more and more. We see these kind of cluster scale structures. And then we can zoom in more on these individual dark matter halos. And so the idea is that these are dark matter halos, and our regular galaxies, like the Milky Way with these beautiful spiral arms, is something that is deep inside these dark matter halos. So something like this, when we look at these galaxies. So there's a tiny galaxy. So what we see is actually a tiny bit, and it's surrounded by these massive dark matter halo around it. And so the dark matter is invisible, right? We don't see that. So we can just turn it off. And that's what we see. But wait a second. So there was a little bit more to it, right? The dark matter wasn't really smooth. Why is it that all these other dark matter clumps that are around it, they don't have a galaxy in there? So shouldn't they have all the tiny galaxies in there? That was the theory, right? That big dark matter halos have bigger galaxies, smaller dark matter halos have smaller galaxies in there. So in fact, when we look at the predictions of cold dark matter, which is our standard theory of dark matter, the standard model of cosmology, we predict that the Milky Way should have something around 30,000 dwarf satellite galaxies around it. Just like the picture here, many more. So today I spent probably half an hour copy pasting the galaxies here. I could not do 30,000. At some point I thought I should just, do something else. In reality, for our Milky Way, we have only observed something around 50 galaxies, 50 dwarf galaxies. So there's like something around like a factor of 1,000 difference between what we actually see around the Milky Way and what these models of like whole dark matter predict. So, call 911 crisis. People throw conferences, cosmic controversies. They say, is cosmology on the verge of a fundamental description of the universe, or is it on the cusp of a major disruption and, well, catastrophe? Right. So what could be going on? So, does anybody want to have a guess of what are the possible solutions to this?
Collisions and smaller galaxies.
Collisions? How could collisions kind of remove them? So merge them together when we're going to see the dark matter surround them.
Collision and merger.
And merger. The mergers that do happen, so we can account for that. So if there's mergers of galaxies, then there will be like bigger galaxies. It kind of changes the kind of like, instead of smaller galaxies, there would be bigger galaxies. But here we're like suppressing everything. Like there's fewer of everything.
The distribution of the dark matter halos could not be the same as in your simulations. If it's distributed differently, the formation of galaxies will be different as well.
Yes. So that's like one of the scenarios, right? There's like two different possibilities here. One possibility, going back to the light bulb analogy, is that we have a lot of light bulbs that don't have any filaments in them. Because we said that we're under the assumption that galaxies, they form in these dark matter halos everywhere. Like small galaxies in small dark matter halos, big galaxies. But what if we have dark matter bulbs and don't have any filaments in them? So now we're going and counting the number of filaments, the light bulbs that we can see, and we're inferring the number of light bulbs, but that may not be accurate because maybe not every dark matter halo has a galaxy. So maybe cold dark matter is fine. We just need to revise our understanding of galaxy formation, how galaxies they form in these dark matter halos. But alternatively, another explanation is that these just light bulbs, they don't exist at all, right? And that was kind of like something like Katelin showed us with neutrinos. There are alternative dark matter models like the warm dark matter, and that have a different prediction for how dark matter is actually distributed. So you have fewer light bulbs altogether, no glass, no filament altogether. Okay, so what can we do? Ideally, all we have to do is measure it, observation, right? If I can look at this image or this image, and see which one it is, we're done. We can figure out which dark matter model it is. And that's really amazing because that can teach us something about the fundamental dark matter particle, maybe, because of how it's distributed. But how do we do that, right? How do you know if there's a glass bulb that's not emitting anything? Any guess? How do you know there's a glass bulb here in the image?
You see a deflection of light.
Yeah, so there's two things happening here. One is there's deflection. So there's like something in the back hitting the light and coming to us. So that doesn't happen with dark matter, right? Dark matter doesn't deflect light in terms of just like bouncing back.
It affects it gravitationally.
But gravitationally, exactly, that's the thing. So these light bulbs here are actually, look at it, it's distorting the image of the background wall. And so it is really through that distortion that your eye picks it up and knows that there's something there through this distortion. And we can do exactly that with these gravitation, with dark matter. And that's what strong gravitational lensing is. That's my field of research. So what is strong gravitational lensing? Katelin showed us. So here we are on the Earth. We're looking at a distant galaxy that could be like 4 or 5 billion light years away from us. And then behind that galaxy, there's another galaxy right sitting behind it. Could be like 10 billion light years, away, right sitting behind. And as the light rays of that background galaxy, they get close to this one, they get bent by gravity, they come to us from different angles. And from our kind of like vantage point, as a result of that, we see light curves from the multiple angles coming to us, and we see these kind of distorted structures, right? Kind of warped, kind of picture of the background galaxy around it. So that's fun, right? So by the way, this was a WebGL implementation of this that I wrote with ChatGPT. So, it's gravitational lensing, strong lens. It's a little bit like looking at an image of a fish at the corner of a fish tank. If you ever notice, you can see two images of the same fish. That's because the light rays from the two sides are hitting the sides of the fish tank, and because of refraction, they're coming to us from two different angles. And so we see two different images of the same fish. Here's a little demonstration of that with Mr. Mango. So as he goes to the corner, you see two different images, and that appears very simple, but you have no idea how long I had to wait for that moment. So here is an actual strong gravitational lens in the sky. You see the same thing. You have this lensing galaxy in the middle forming two different images of this distant quasar. And these are like, it's fascinating. I mean, we see two different images of the same quasar in the background. And when we look at galaxy strong lenses, where both the background and the foreground, the lensing structure are galaxies, you see these kind of like distorted structures. Same lens that Katelin showed. This is a beautiful lens called the horseshoe lens. So you see this like lensing structure, and then behind it, there's a galaxy that kind of looks like that maybe. And that galaxy, just because it's behind, is kind of stretching to this beautiful arc. And the reason that we see these arcs is just the geometry of lensing. You know, you can get a wine glass at home, and after drinking, put it in front of a candle flame. And so you can see this sort of arcs very similar to the gravitational lenses that we see. So in this analogy, the background galaxy is the candle flame, whose image has been distorted into these arcs, and the foot of the wine glass is the lensing structure that's kind of like bending space-time. But what do we want to do with this? Well, that's the whole galaxy there, bending the light. What I'm interested in is a little water droplet on the foot of the wine glass, right? We're interested in these tiny dark matter subhalos, tiny dark matter halos, like tiny satellites of these galaxies. The main galaxy is the foot of the wine glass that's doing this massive distortion to the images. But if there was a tiny water droplet, that water droplet itself does a tiny distortion to the image. And if we can quantify these distortions, we can hope to find these tiny, tiny clumps of dark matter, regardless of if they have stars and gas in them or not, because we are only measuring them gravitationally, right? So that's the hope. The idea is that if these galaxies have a lot of dark matter subhalos, when they lens the image of background sources, gravitationally, they would have an imprint in the images, and we can detect those imprints, and then we can try to kind of have a statistical measurements of that. So here's the thing. This is a little simulation. If I put a dark matter halo, like a subhalo, tiny one, on top of one of the images, it's going to kind of distort that image in a particular way. This is a simulation. And so it can allow us to detect it. But the problem is that it is really, really subtle. So here's a simulation written by one of our postdocs. And so here you can see a background galaxy. It's being lensed into these arcs that you see here. And the dots here are the positions of these dark matter subhalos as predicted by the cold dark matter model. And every time that we're pressing the button here, we're getting a different realization of these things. And because it is a computer simulation, I can turn off the stellar light from the main lensing galaxy in the middle. So we only see the distorted image. And so look at it, every time that we press it now, we see tiny, tiny distortions in the images. The images just jump around a tiny bit. And that is the result of like tens and hundreds of these dark matter halos being there collectively. So it is a very, very difficult task to actually extract this information from the data. But how do we do that? We extract this information from the data by first being able to simulate the data, which means in a computer, we want to have a model of the data. And for a gravitational lens, we need to figure out two different things. What does the image of the background source actually look like? What is the undistorted image of the candle flame? And what is the shape of the foot of the wine glass? And if you know these two things, we have figured out the whole system, right? And we can simulate it, and the simulation is sort of easy. So if you give me a foot of a wine glass, I can just go and solve and figure out where everything came from. So at one point where I'm looking in the sky, I can calculate a deflection angle, see, oh, this point actually came from somewhere else. And so with that, I get some sort of like what is called a vector field, kind of like a bunch of arrows that tell me where things came from. So then I can get the image of the candle flame and move every pixel according to that, and I get, something like that. So a little bug, we have this like package called caustics that our group has developed. And it is a package for, scientific kind of research that simulates these gravitational lenses. But for fun, there's also a kind of like interactive, API to use it. So if you go to the QR code that is here, you can actually kind of like play with it to see how you can produce a gravitational lens by changing the parameters and what it looks like to give it an intuition. But the problem is that when we look at our observations, we don't know what the background source looks like, nor what the distortion is, right? We have to figure them out both at the same time. And we don't know, what is the inverse of their simulator. So we solved the problem by simulating a lot of, things. If I can produce a lot of simulations, computer simulations of different candles and different, kind of like, feet of wine glasses and put them all together and go through millions and billions and trillions of them. And if I find simulated images that really look like the observed data, then I can say, things that I found there that I had there, they must be the correct description of the background source, right? And the foot of the wine glass. And we do the comparison for these things with something called the likelihood function. So this is something that I was doing for many, many years. Back in 2016, we analyzed this gravitational lens, and we found the evidence for the existence of a 10 to the 9 solar mass subhalo at this location. And so this was really exciting at the time. It was like, press coverage of this thing, the hunt for invisible dwarf galaxies. But we had to use 2 million CPU hours and a year of analysis for this one gravitational lens. And so I kind of felt at the end of this is like really not scalable. This is really not feasible, given that we're expecting to have hundreds of thousands of gravitational lenses that are going to be detected with new experiments. So what's the answer? AI. Hate to say this, but we were doing AI before it was cool. So this is back in 2016, 2017 is when we started doing, machine learning. And I don't get into the details of that, but you've all heard about, neural nets at this stage. So you can imagine that a neural net is this computational structure that gets input data, in this case, like digits of handwritten, kind of like digits, images of handwritten digits, and it passes them through some layers of computation to make predictions for, what it is. So in this case, if it's a digit 6 or 7 or 8. And we just thought we can do the same thing. We can just like put images of gravitational lenses into our neural nets, have them process them in many layers, and at the end make predictions for the things that we care about. For the dark matter halos, or reconstruction of the images of the background galaxies, things like that. And so what we found was that yes, it was possible, and the amazing thing about it was that we could do this like millions of times faster than what we were doing with these traditional kind of models that were just like producing a lot of simulations for every analysis. So ever since then, all our group has been kind of just like going in that direction of developing machine learning model and artificial intelligence for the analysis of this specific problem. These are, some of the people in our group and our kind of like newly founded institute in machine learning and astrophysical data analysis. And so the question is, where are we now? I don't want to go into the details, but we've had a lot of success into being able to harness this kind of like powerful machinery of machine learning to solve this problem. So here's an example of getting these gravitational lenses in data and then predicting both what the matter density in the foreground is and what the image of the background galaxy is, and simultaneously, figure them out. But a lot of the work is actually into kind of understanding the uncertainties and the robustness of these models. It is one thing to just use machine learning for classifying cats and dogs. It's another thing to use it actually, in a kind of a scientific domain where uncertainty is really important. So if I say that I'm confident with 99.9% that my conclusions are correct, I have to show that I'm actually 99.9% correct and confident and not a little bit less or a little bit more. So our recent work is kind of like managed to apply this to actually real gravitational lenses. These are kind of things that we haven't published yet, but I'm really excited to perhaps come to results on kind of observational results on this within the next couple of years. So stay tuned. Thank you.
Thanks to both speakers for these very interesting talks. So now we're actually gonna start the panel discussion. So I just want to make sure that everyone can see for the live streaming. So maybe. I think maybe if they, yeah, maybe it will work when you're sitting there. Yeah, the problem is I would need to put it, wait, I need to put it. Yeah, no.
360 like this, but not like this.
Yeah. And then if I put it on the chair, yeah, it's not long enough, so maybe. Actually, I think it's okay. It's fine. Sorry for this technical. Okay. Okay, I think that's good. So if it's stable. I think, are we happy with this?
Yes.
Microphone? Okay, great. So yeah, thanks for being here. So now we have some time to all ask questions. I would like to start the panel with a question, namely, so what do you think are like currently the biggest challenges when it comes to dark matter research? And what are some like upcoming experiments or like some technologies you're really excited about? Yeah. And for the YouTube audience, if you have a question, feel free to type it in chat and we will be with you. And who wants to start? Start. Okay, Katelin. This is okay. Yeah, no, it's
Personally, for me, in my opinion, I think one of the major challenges is just such a wide range of possibilities for what could be dark matter that it makes it very difficult to know, how should we best focus our efforts? Like, what is the organizing principle that we should use to, plan some sort of mode of attack? And you might think, okay, yeah, this is a broad question, but really to quantify that, if we were to assume dark matter is one thing, which it may not be, it may be multiple things, but if we just for the moment assume it's one thing, and we ask, okay, well, how massive could that one thing be? It turns out, from observation, the constraints are such that it could be anywhere within 90 orders of magnitude. So that's a one with 90 zeros behind it. Okay. So that's a very daunting challenge. So for me personally, I mean, there's different ways of organizing things that you can think about. Maybe you want to organize things by how theoretically beautiful some ideas are. Maybe you want to, go for the more beautiful ideas first. Maybe you want to focus on ideas that solve other problems. So the standard model of particle physics, which is just a fancy name for the Venn diagram I showed. There are other issues with it aside from missing dark matter. So maybe you try to kill two birds with one stone. You try to make your dark matter also address any other issues that we're currently experiencing with the standard model. That's another guiding principle. For me personally, I like to focus most on things that I can imminently observe. So things where, I can treat the universe as this experiment that's telling me about the nature of dark matter, and I can then just go and look for it. So, I think it takes all kinds, but it is certainly a very daunting challenge. And I think everyone who thinks about this question has to grapple with, the real possibility that you may spend a career thinking about different kinds of dark matter candidates that may have nothing to do with the universe that we live in. And that's a very real thing. It's a privilege to do it, but, some days I'm like, well, what makes me, different from someone playing games all day, right? Because it is very fun to think about these, but I think we are learning a lot when we ask questions about dark matter. We're learning a lot in the process. So, Edison said, about all his failures, like, oh, all these failures weren't failures. I just discovered a bunch of ways not to make a light bulb. And, you know, so in the process, you learn things. So it's about the journey, not the destination, right? That's my 2 cents.
Yeah, I think the biggest challenge is kind of that we're just stuck. And we've been stuck for almost a century. A bit less, okay. I mean, the thing is that it's sort of from an astrophysicist point of view, I think dark matter is one thing that we have to acknowledge, that there's like multiple communities that are interested in dark matter, from particle physics, fundamental physics, and astrophysics and cosmology. In the astrophysics world, you know, the topic that I'm trying to explore seems to be one of the sort of few remaining tests that we think, okay, I mean, people try to come up with tests, but we've done a lot of these tests, and everything seems to just point out to, yes, there is a particle, yes, it has gravity. And as of now, we haven't found anything except for the fact that, yes, there's something that has gravity. So we get very excited for any possibility of new tests that just can shed light on something about it, you know, point out to some direction of particle physics or fundamental physics, what it is. But there's not that many left, because we've already tried a lot of things, and that's what we have found. So I think that's for me is kind of like the challenge, but it's also, you know, that's just what it is. I'm glad there's a few things left, because otherwise I would be jobless. So and in terms of new avenues, that was your other part of the question, I think. So as you saw, kind of like my aspect of kind of like my work kind of relies heavily on data analysis, and so we get the data and try to extract the information out of it. And that's kind of like the thing that mostly, you know, I'm excited about, especially with this artificial intelligence and machine learning. There's really a new opportunity and possibility to extract information in a much more accurate way, in a much more detailed way, like extract the full information of the data, and to do it much more kind of like, you know, accurately compared to some of the things that we were doing before. And that is true across like all of astrophysics, I would say, and perhaps other fields. So it's very exciting, that aspect of it, but it's not guaranteed to necessarily, you know, reveal anything. So if hypothetically dark matter ends up being the same thing, and we find that we did a really fantastic job at analyzing it, and then that's the same, you know, thing that it is, and that's what it is. But for now, it's very exciting, because every day we are finding new ways that we can actually extract information that was like so difficult to extract before, and we can do it more and more detail, and that's really exciting right now.
I want to maybe, before you folks ask your questions, I also want to maybe inject a little bit of optimism into this, because it's true what was just said. You know, the guy who coined the term dark matter was this like very cranky Swiss astronomer, and that was in the 1930s. But people thought, oh yeah, cranky Swiss astronomer, okay, you have your little dark matter, but astronomy is really hard, right? So we don't, okay, that's cute, but we don't really believe, like people didn't really take that super seriously. Rubin came along, again, that was 50 years ago still. Okay, people started taking it more seriously, but then thought, okay, well, maybe we just don't understand gravity that well. But, you know, really a lot of the pieces of evidence that I showed for dark matter during my presentation, I didn't put the year, maybe I should have, because I do want to emphasize that that is actually the byproduct of, you know, really modern technology, and just the exponential growth of the amount of information we've had. So the merging clusters, we saw that movie, that's 2007. Okay, so less than 20 years old. Cosmic wave background, those sound waves, okay? The one I showed you, that was 2013, okay? And actually the first detection of those sound waves and seeing kind of the full ripples, that was the early 2000s. So really, you know, this is like, we had this concept of dark matter, people didn't really take it that seriously. It took all of these independent probes for people to really say, okay, something's really happening here. And so that's why I'm actually optimistic about this problem, because we're still riding that really exponential curve, I would say. So I think it is a really hard problem, but there are also reasons to be optimistic. Sorry, just want to interject with some optimism.
And I will have a last question, and then or yours. So do you think there are currently big discrepancies between theory, experiment, and now, I guess, computational work when it comes to dark matter? And is there in the future maybe the probability that this discrepancy are going to like diminish? Oh, I think I'm gonna go first since I want to.
Sure. So it's kind of an interesting thing. The thing is that the way that we do astrophysics has really radically changed over the past, like 30, 40, 50 years. I kind of imagine that, maybe in the 60s, astrophysics was at a stage where people kind of, would look at the data and immediately, with like a pen and pencil, be able to kind of just like come up with something amazing and write it like in a 3,000 sided paper. And in the 80s and 90s, I think computers became more widespread. And so we went to this sort of statistical analysis. And so it was nothing, we kind of like took all the kind of like low hanging fruits were done. So now we had to kind of like work harder. So to kind of extract information out of something, we had to get the data and do statistical models. And yet those statistical models were still somewhat simple. So we were still, again, cherry picked. So I don't want to get too technical, but we had models that were sort of like easier, power spectrum analysis for maybe some experts. So things Gaussian, kind of assumptions in it. And now more and more, we kind of like have kind of taken kind of like some of those like easy stuff. So we're trying to push to kind of like harder and harder computational things. And to extract the full information of the data and a lot of data. So now we're in an age of this kind of like data-driven astrophysics. We have surveys that are scanning the sky, giving us a lot of data. The Vera Rubin, observatory, the LSC survey, starting next year, Euclid kind of, space telescope, like just started observing like last year. And they're like scanning the whole sky, like a survey, like a map of the entire sky at like resolutions, for like Euclid comparable to the Hubble Space Telescope. And other things, 21 centimeter data, cosmic microwave background data. And so there's a flood of data that is coming, and we need to extract a lot of information out of this. And as we do that, we just realize that our theoretical models, and these theoretical models, I don't mean necessarily about dark matter, but simple things about the physics of gas and radiation and sound waves, and et cetera. We just realized that we need to be very, very accurate about our predictions, because otherwise we're going to confuse ourselves, right? So the easy stuff was the things that was just going to be so obvious, be like, oh, are there some kind of like bending of space-time at very large scales, or is there something, the number of galaxies, kind of first order kind of thing? But once you kind of start getting into the kind of the details, then you have to be very, very, very careful about all of the assumptions. And I think that is kind of like an aspect of the field that we're just realizing that what we call like baryonic physics, the physics of regular matter, understanding it and being able to predict it very accurately and precisely is really important for us to be able to extract these detailed information out of the kind of the flood of data that is coming.
Yeah, I'll echo that and just say the more data you have, the more opportunities there are for there to be some kind of an anomaly, right? The odds that, a golf ball will hit a particular blade of grass are very low, but the odds that a golf ball will hit a blade of grass are basically 100%, right? Unless you're a really bad golfer like me. So, if you try enough times, if you have enough blades of grass, the golf ball's going to hit one of them. So you're going to have something funny happening, some kind of anomaly. And historically, in searching for dark matter, that has happened a number of times. And kind of referring back to what I said before, and it really is, I said it kind of sarcastically about, oh, it's the journey, but it really is true. So, there have been a few examples in astrophysics where, something looks weird. We were looking for dark matter. We saw something weird. We thought, aha, this is certainly dark matter. And then we dig a little bit deeper and no, it turns out, oh, galaxies form in this weird way, or, oh, like one really weird one that happens, like maybe 10 or 15 years ago, we saw these bubbles of radiation coming out of the galactic center, these big honking things. Thought, oh my God, what is this? Like, this is not, doesn't correspond to anything. There's no stars. What is going on? It turns out, actually, we think it's related to the physics of basically the supermassive black hole in the center of our galaxy burped maybe 100 million years ago. we're still trying to figure out exactly what happened, but we now know pretty confidently it's not dark matter. But actually, still to the present day, we have these anomalies. So one other example related to what's happening in the center of our galaxy is we do have this really persistent excess of gamma rays coming from the galactic center. And some people think maybe that's evidence that dark matter is annihilating. And actually, some of our simplest models of dark matter do predict that that should happen. So some people are very excited about that. Other people are like, no, it's definitely not dark matter. It's probably a bunch of pulsars, which are these objects that can emit gamma rays that can mimic what dark matter would do. So, we have to still dig deeper on a lot of these ongoing questions, but again, it's really about the process. So even if that ends up not being dark matter, maybe we learn something about these gamma ray pulsars. So there's tons, and I could go on and on and on. There's tons of examples like this. But yeah, I think that's what makes this really interesting and spicy, because, if we didn't have all this data coming in, and if everything was just matching like what we thought, then yeah, then like Yashar said, like what,
It would be boring.
it's boring, and why do I have a job, so.
Thank you. So now we have time for questions. Okay. Do you want the microphone or?
That's okay, I can speak. Alana, first of all, thank you very much. Great presentation, both of you. Two quick questions, both related. You say that there's a whole bunch of ranges of what dark matter could be, but surely based on limited observations we have, there are some things that we know it cannot be. For example, you showed a simulation where you said if it was neutrinos, it would look like this, and it doesn't. But I guess in that simulation, we are assuming some properties of dark matter that are not neutrinos, because otherwise it would look the same, right? And the other one that comes to mind, one of the, I guess, the very basic observations is that the galaxy rotation curves imply a sort of distribution of the disk of dark matter that's sort of like less dense in the center than as you go out. What properties does that tell us about what dark matter would have to have that clearly is different from baryonic matter?
Yeah, great question. So Yashar mentioned this the kind of null hypothesis, or our default assumption of what dark matter is, and that's a paradigm called cold dark matter. And what that basically means is that we just assume dark matter, it's going slow. Okay, so like neutrinos are going really fast, and the fact that they're going really fast is why we know that they're not the dark matter. If things are going fast, you can't, form all these little clumps. So yeah, it's cold, aka slow. And it's collisionless, so it's not interacting very much. That is always kind of that's the gold standard, that's the null hypothesis against which we can compare. So now cold dark matter makes these certain predictions. Usually we're, starting our simulations assuming that. But for people like me and my collaborators, a lot of us are actively engaged in saying, well, let's do a simulation where we don't assume that. Let's try to assume that dark matter is something else and see what happens. And indeed, you can actually affect how many galaxies we see today, and you can affect not only how many there are, but also, as you alluded to, the kind of shape, the morphology of how that matter is distributed. So for instance, some theories of dark matter predict that there should be a very sharp drop off in the density, whereas others predict it should be pretty gradual and pretty smooth. So, and that has to do with properties about like, is dark matter interacting a lot with itself perhaps, which is a really interesting possibility. So there's a lot that, as we try to spatially map out the dark matter through these methods that Yashar and others are pioneering, we can infer then, what would have been the initial conditions, or what would have, how would we have had to have started our simulations in order to be consistent with observation. So that is a very real possibility. It's one that people are very actively exploring, including me and my group and our collaborators. So yeah, it's an excellent question. And I think one thing that's really important is, again, it's not like, I'm stroking my beard and thinking about my very favorite string theory, whatever model. It's really, basic phenomena. Does dark matter do this? Does it interact? Does it scatter? Does it annihilate? Does it decay? How is it behaving? So when you ask those kind of very coarse-grained questions like that, you can really make a lot of progress in attacking different models.
Yeah, I think that kind of like explaining. So, I think the way that the field kind of works is that you have people like Katelin that, from a theoretical perspective, kind of propose, be like, could dark matter be such particle that has such and such property? And so these sort of like properties at the particle kind of level somehow miraculously actually changes the way that dark matter should be distributed in the universe. And that because early in the universe, when the universe was much, much smaller, this dark matter would have had some interactions with other things and it would have been distributed. And so the result of that is that today when we look at it, it would be. And so people come up with these theories, and then some people like me, they say, okay, let's test these theories with some observational thing. And so this has been going on for decades now. And there are dark matter candidates that have been ruled out. Like, so there have been throughout this journey, there has been a lot of dark matter candidates that somebody proposed. Like back in the 80s, people thought that just regular neutrinos could be like all dark matter. And then very quickly we realized that that is not possible because you wouldn't have as many galaxies as clustered as they are now. So that's ruled out, et cetera, et cetera. So where we are kind of left with now is that there's this like kind of, kind of our default model, cold dark matter. Cold dark matter from our perspective is basically just saying dark matter just is particles, has gravity, and nothing else. And we know that this is an idealization. At a particle level, this has to break at some level. Everything else that we know about physics at some level breaks. When things are in extremely dense environments and extremely hot environments, eventually there's interactions with other things. So we just realized that cold dark matter is really like a cartoon of something. We just say that if it has any particle properties, it's just below what we can see its effect in the distribution of the universe. And so today we're in this regime where we're saying, okay, there is still a bunch of candidates, cold dark matter and a bunch of other candidates, self-interacting dark matter, warm dark matter models with a certain temperature, et cetera, that still kind of like observationally, we cannot rule them out yet. And that's what we're trying to do. And kind of just like, and I think, there might come a day where we're just saying that astrophysically, kind of anything that we have kind of just like gone through everything. And as far as astrophysics is kind of like involved, dark matter is cold. So it means that there's an upper limit. This is that any particle properties that it has is astrophysically just like not reachable. And now we need to go to, kind of collider experiments or other direct detection experiments or other ways of probing dark matter. But we're not there yet. So there's still kind of like a part of this parameter space that's left for exploration.
Yeah.
What about the observation and the weight, the uncertainty on the base, the space?
I didn't quite hear it.
Gravitational waves. So do gravitational waves have anything to say about dark matter? Maybe.
Yeah, so I think what the question was alluding to is this phenomenon called gravitational waves, where if you have something massive that is bending space and time, and if you wiggle it around, then the bending of space and time is kind of like the ripples on a pond, right? So you can actually create a wave of those bends in the fabric of space and time. And so that's exactly what was discovered for almost 10 years ago now by this team called LIGO. And it was super exciting. They discovered two black holes that were, in the final phases of merging together. And that taught us a lot of really interesting things about gravity, right? So actually, something I alluded to during my talk is like, we have all these really great tests of gravity. So we're pretty confident again that, this phenomenon of dark matter, it's not that we don't understand gravity very well. All the tests we do of gravity, including the existence and the properties of gravitational waves, those are further and further confirmations of our theories of gravity. So those observations are very helpful for that purpose. You can also be very, like I said, you can be very creative. It's a big universe, you can play around. There definitely are theories of dark matter that can create gravitational waves. It's very hard to make them at the level that they are currently observable. However, one thing that's really exciting that many people in my field are thinking about is the fact that whatever was responsible for making dark matter in the early universe, it could have been as the result of a phase transition, which would actually create a lot of like a background of gravitational waves. And a lot of people are excited about this upcoming mission called LISA, forget what LASIK stands for, but it's basically like LAGO in space. So the idea is you launch a bunch of lasers in space and you create an interferometer that's many, many kilometers long. So you have this one laser goes like this and one laser goes like this, but in space, and you try to very precisely time how far or how long it takes the laser to bounce back and forth using this technique called interferometry. And essentially with that, you can then try to look for these very, very faint gravitational waves that could have been the remnants of a phase transition in the universe that could have created dark matter. So many people are excited about that possibility, but with currently observable kind of current, maybe if you do something really weird with the dark matter, so maybe something a little bit, very creative, you can do something with the current observations, but it's difficult. It's difficult to do that in a way that's consistent with the other observations that we do have.
Yeah.
In the merger slide, you showed that the regular matter in pink was slowed down due to viscosity and it dragged, whereas the dark matter would keep going. Does this imply that the dark matter doesn't interact much with itself?
Ding, 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 ding. Yes. In fact, that is one of the strongest limits that we have on whether or not the dark matter can interact with itself. And you can actually derive, an interaction rate, or oftentimes in particle physics, we parameterize it as a cross section. And I kid you not, the units that we use to talk about these cross sections is called a barn. Okay, because it's like you can hit the side of a barn. Okay, that's a barn is a big cross section. For context, so for the Higgs boson discovery in 2012, that was around 10 to the minus 11 barn. The constraint we can set from the bullet cluster, 1 barn. So, not a very tight constraint, but a very important one nevertheless, and it is informative about many theories of dark matter. So yeah, it is very helpful. There are other ways you can try to look for dark matter self-interaction, a bit more subtle. That one's very literal, right? You're really ramming these two clouds of dark matter together. So that one's very unambiguous. Yes. Yeah, great question.
I think the animals are safe. We shouldn't worry about dark matter.
I don't know who's moderating.
Yeah, you are.
So as of right now, like how much do we know like about the distribution of dark matter locally, like in the galaxy stuff? Like in a galaxy, like if I hold up my hands, like am I by chance touching some dark matter?
Yes, I wouldn't worry about it though. Yes, so, I mean, dark matter is, as far as we understand, dark matter is here. Dark matter is around us, so there's dark matter particle here. But first of all, as was mentioned, it doesn't interact much with itself. It doesn't interact much we don't know to what level it interacts, but it doesn't interact much with anything. And dark matter is not the only thing that is like that. I mean, I just want to kind of like support some of like kind of Katelin's kind of arguments about the fact that it sounds science fiction, but and I think when I got into this field, I kind of felt like that for a long time. I felt like this sounds all like gibberish. We just made up something. But then you just realize that there's something called neutrinos, and we have detected it, and it's so hard to detect. Every second right now, there's like gajillion kind of neutrinos going right through our bodies. From the other side of the earth, it goes through the earth, from the sun, comes through the whole earth, and then through our body and goes, and it doesn't interact with anything. It's so hard to kind of capture them, and now we have captured some of them, so we understand that they exist. And so, yes, there is dark matter, and there is dark matter locally, and there's dark matter kind of throughout our galaxy. But the thing is about dark matter is that it is very diffuse. So if there's particles, it is not at structures, kind of like, say solar system or our solar neighborhood or whatever. You're not going to find like, a bunch clumps of dark matter, because exactly the only way that it kind of interacts with itself is gravitationally. And so it's kind of like quite diffuse. So just think about it. Now there's a lot of dark matter in the universe, much more dark matter than regular matter. But this dark matter is so spread out, kind of thin through the universe and through the galaxies and everywhere. Whereas the regular matter, because it can emit radiation. So as gas and things like emit radiation, like they kind of cluster and they become kind of more dense. just become colder and they become kind of more dense. And so baryonic matter is like very kind of condensated and very local and very high density, whereas this dark matter is kind of diffused throughout our galaxy. So it's on much larger scales, like the clusters that I was talking about, kind of these clumps of dark matter that we hope that we can detect gravitationally. But that's part of the reason that it's very hard to detect them, because they're just so diffuse. So we're looking at these tiny perturbations that they might cause in the images.
You're actually looking at the person who, to my knowledge, made the most local measurement of the dark matter density. The measurement that I did, and so yeah, this is like, even though, yeah, as Yashar alluded to, I'm a theorist, but the on-ramp, if you want to like get in there with the data, the on-ramp to thinking about different kinds of theories of dark matter is a very short one. So even theorists like me can actually do a data analysis. And I did one back in 2018. And why were we looking within 100 parsecs, which is around 300 light years? We were actually looking, this is alluding back to a previous question about the shape of how dark matter is distributed. What we were looking for actually was a really thin disk of dark matter. So the halos that we saw in the simulations are these big puffy blobs, right? But you can ask the question, well, our Milky Way looks like a disk, okay? And so why couldn't the dark matter also look like a disk? And so you can theorize and think about different, theories of dark matter that might behave that way. And someone even wrote a book about how this might have led to the extinction of the dinosaur. I'm not kidding. This is a well-respected scientist in my field. Like I said, there's a lot of room for creativity in this field. It's not a very big on-ramp to get involved and get your hands dirty. But yeah, so to my knowledge, that was the most local measurement. So it's like a box, that's 300 light years across. In principle, there doesn't have to be any dark matter in this room. In principle, we can't say for sure that there is, because again, we only know about the gravitational interactions of dark matter, and gravity is very difficult to measure on the scale of this room. We can measure it, when we have a lot of dark matter accumulated over, hundreds of light years, but it's very, very difficult. So actually, very fascinatingly, there are some theories that predict that in the very early universe, the dark matter actually should have clumped up into these little, they're called microhalos. And they're kind of like this, they're similar to the mass of the Earth, but they're really puffy and they're kind of distributed all throughout. So on a scale of like 300 light years, it would look identical to actually, the dark matter, the cold dark matter that we know and love. But yeah, there might not be any in this room, but you have to do something weird to the dark matter to make that not be the case. Kind of conversely, you can ask the question, okay, given that, Katelin Schutz made this measurement of the density of dark matter in a 300 light years box, kind of what's the average spacing between particles of dark matter? And if the particles have a mass that's similar to the mass of the atom, the answer is the typical distance between those dark matter atoms is about 1 centimeter. So this room would be filled with, dark matter, if that were the case. If you make the dark matter even lighter, again, because we can measure the mass density, that's the thing that gravitates, but the number density, you have to divide by the particle mass. And the particle mass, as I mentioned, can span 90 orders of magnitude. So if the dark matter is much lighter than that, there could be 10 to the 90 dark matter particles in this room. Or if the dark matter is much heavier, then there could be no dark matter in this room. So it really, really depends. And again, we really can learn so much about dark matter if only we can understand how it's spatially distributed. There's so much to learn.
Is there any way that we can determine if dark matter affects or alters time in any way?
Well, it will. So again, Einstein's theory of relativity tells us that anything that has mass, aka that includes dark matter, it's going to bend space and time as fabric. So it can affect time in that sense. In the theory of relativity, you get these effects where it's called time dilation, like time can seem like it's going slower. Maybe you've seen the movie Interstellar, right? They go down to that really dense planet where there's a very strong gravity and they come back and their friends have aged. So dark matter can in principle do the same thing. Again, it's just consistent with Einstein's theory of relativity, but it's not something special about dark matter. It's anything that has mass will do the same thing.
No, I don't have anything to add to that. Yeah, as Katelin said, as far as we know from a theoretical perspective, dark matter has mass because it has gravity, that's the way that we know that it's there, and so it kind of, general relativity, kind of tells us that yes, it contributes to the bending of space-time and that's what it is. But I wanted to kind of like point out something kind of like slightly irrelevant, but very interesting is that, so you remember that I showed you these like images of gravitational lenses. When I showed the fish tank, and at the bottom, there was like two images of the same quasar. One thing that is really fascinating that kind of relates to this thing is that these two different images, we don't see them at the same time. Like, so they are showing the image of the background quasar at slightly different times. So it is like you're passing by on the street and you see me, and then all of a sudden you see two images of me next to each other, and you're like, oh God, I mean, one of them, I'm kind of like a few years younger. And or maybe a picture of me. And this is really fascinating observation. We know this. So we see explosions going on kind of just in these background sources. And then we see it in one image, and then we have to come back weeks or months later, and then we see it in the other image, and then going on, which is just like fascinating to see this kind of really bending of space-time actually observation to see. It's fascinating.
Yeah, are we certain that dark matter and normal matter will evolve together at the same time? Or could dark matter be a kind of byproduct of normal matter? Because if we watch the kind of big spider that you were showing, the dark matter seems to be away of the center. So like a byproduct.
I kind of see a question for you.
Yeah, great question. I love this question. So, again, empirically, I like to come at it from that angle. We know that there had to be dark matter as early as, sorry, I think in cosmologist units, which is redshift, and I have to convert that to time, which is not always easy.
300,000.
Well, that's the CMB, but matter radiation equality was even early. I'm gonna call it 1,000 years. Let's call it 1,000 years, plus or minus an order of magnitude. What's an order of magnitude between friends? So it had to be there at least that early, but it was probably there earlier. And the reason why is that, as you alluded to, something had to make this dark matter, right? It can't have just popped out, right? There was some process that it was made. And many of the simplest processes that you would think about that could make the dark matter, if they don't happen super early, like I'm talking less than 1 second after the Big Bang, then if they don't happen that early, then you're going to mess up a bunch of what we see. The sound waves in the cosmic microwave background, for instance, very easy to mess that up. So pretty sure it happened in the first fraction of a second after the Big Bang. And indeed, like if the dark matter and regular matter can interact at some very tiny level, then it is possible that you can kind of convert from regular matter into dark matter. In fact, some years ago, I wrote a paper, this editor's suggestion, so it's one of my most famous works where we had this exact same idea. So you too could be a dark matter scientist, very cited work. We actually proposed you could make dark matter out of light, which sounds really crazy. But actually the reason why it's possible to do this is because in the early universe, light's not just propagating freely. It's actually being slowed down by this plasma, right? It's hitting all these electrons and it's kind of acting as if it's heavy, right? It's not just zipping at the speed of light. It's kind of like going like this. Formally speaking, it's acting like it has a mass. And anything that has a mass, if it interacts with other things, then it's possible for it to decay. So that is a very real possibility that we looked at. And it's something that people are actively looking for, both with astronomical observations, but also it's testable in the lab. But just to emphasize again how hard this is, in order to make the amount of dark matter that we see, you can kind of frame it like in units of the electron's charge. What would the charge of the dark matter have to have been to make all the dark matter? The answer is 10 to the minus 12. So very small fraction of the charge of the electron. So it's very hard to look for this. We have a lot of ideas, but not straightforward. But yes, excellent idea. That's something people are actively thinking about. Yes.
If dark matter only interacts with gravitational, can it fall into a black hole?
I think it's your, I don't know, I would say, yeah.
Yeah, it could fall in. I will say, actually, it's a lot less efficient at falling in than you might think. You might think, oh, it has all this gravity, so yeah, it can just get sucked in. It turns out though that, so, you know, I really like this analogy of the light bulb, because the spatial difference between the whole light bulb and the filament is actually very similar to the actual spatial difference between dark matter, big puffy blob, and the galaxy that lives inside of it, which is relatively compact. And the reason why the regular matter can be so compact is because it's able to radiate away energy. And so it's radiating away energy, okay, and it's, not able to go as fast, and so gravity can pull it in more, and it radiates away more energy, and so it's slowing down again, so gravity can pull it in more. So this is a runaway process that happens for regular matter because it's radiating away energy. But the dark matter, because it's so inert, it's not doing very much, it's not able to radiate away energy in that same way. So it's actually very, very inefficient at kind of collapsing. Yeah. But no, I mean, there's like a lot of different ways, again. I forget who's asking these questions, but they're all excellent. So gold star. But yeah, you can mess up the properties of dark matter in all kind of interesting ways that could enhance how easily it would fall into a black hole. And so then you can try to look for the signatures of that. So if you made it really, really easy for dark matter to fall into a black hole, because of whatever theory of dark matter you have, then maybe you're going to grow these really ginormous black holes really fast, because they're going to be able to eat all of this dark matter and become bigger and bigger. And so that's something, again, that you can go and try to compare and test with observations. And that's something that people actively are working on. Great ideas. I should just mime you guys for all of my ideas in the future.
So we have one question there. We'll just take other two questions and then we're gonna end the panel. I think there was a question.
Just starting with leadership. If you had one of these, unlimited budgets for your next research project, software, hardware, where would it go?
Yeah, I'm very biased about that. I think that, as I mentioned, I'm very excited about machine learning and data analysis. The thing that we have discovered the past few years with this thing is that the data that we currently have has such a wealth of information already in that we are not completely extracting. And it takes relatively very little kind of investment to be able to, today, given this new revolution and wave in machine learning, I think that we can get a lot kind of, for $1 of investment in kind of figuring out how to analyze data correctly, as opposed to investing the same money into kind of building instruments. Now, somebody has to build instruments and somebody has to so that's a very valuable thing. I think it depends kind of just there's different institutions and different researchers have kind of historically kind of expertise and kind of an unfair advantage in certain things. If I was at, say, Caltech, probably access to a lot of big telescopes and getting more money and putting tens of millions of dollars into another telescope would be maybe not so hard. But I would say that, kind of today, I kind of feel that for kind of dollar for dollar, that if that investment is kind of put into kind of figuring out how to analyze the data, is gonna kind of go really, really far. And yeah, so a little bit of that needs to be sort of in the computational hardware part of it too. We need GPUs. In 2017, when I started doing machine learning, I thought I should buy NVIDIA stocks. And then unfortunately I sold it, and then only has gone up by factor of 3,000. So but there's really a revolution happening on that front. It is just crazy, and I think it's not something. There's just so much. Just given so I'm not talking about the more progress in the field of machine learning. If you just freeze what has been already developed in that front, and we actually start applying that to astrophysics, it's going to take us years and maybe decades to actually be able to adapt these things into kind of our problems and be able to extract it. And it could be really powerful because, we did this paper with one of our students that we just got HST images of a galaxy that had been also observed with JWST. And these HST images, when they just combine in the traditional way and you just look at them, they look completely like crap compared to the JWST images. And we did these kind of methods that we were doing on the HST data, and we were getting basically like as good as the JWST images. It was just like mind blowing that this information was actually there in the HST data. It's just that it is not properly extracted, things with, complex noise or complex kind of blurring and things like that, that these are information that we could actually extract out of the data. And so we've already invested tens, hundreds of millions of dollars to kind of build these instruments. And there's like this flood of data coming. So we need to use them, it's like, we need to extract the information out of that data before we just go and say, let's get more. That's my perspective.
Yeah, I super strongly agree with what was just said. And yeah, I actually would add to it that I think also dollar for dollar, you get a lot out of theory, actually. And I'm not talking, I'm maybe not necessarily talking about the beard scratching kind, like I'm really talking about, figuring out how best to observe these phenomena and these different types of dark matter. Shameless plug for myself, and I see you're sitting right next to Vicky Caskey, superstar astrophysicist and principal investigator of the Time Telescope, which is this amazing instrument, doing all this great science, looking for fast radio bursts and mapping out all the neutral hydrogen in the cosmos. And it turned out, little old me, and I come along and I'm like, wow, all these great people in my department are doing all this great work on chime, and let me learn more about this, and come to realize that this whole time it was actually a dark matter experiment. And it's actually very, very sensitive to a particular kind of dark matter called axions. And it's just that, the right people maybe weren't talking to each other. You kind of have to put them all in a room together and maybe give them some pizza and like let them kind of percolate in order to know what everybody else is working on. And then you kind of come to these realizations like, aha, wow, we don't have to build this, tens of millions or hundreds of millions or billions of dollars new experiment. We can actually just use what we already have. So, in the long run, you end up saving a lot of money that way. And I think also like being very judicious about, like thinking about how we're analyzing the data. That also requires a lot of like theory, people, really at the forefront thinking about different statistical methods, including AI, but not limited to AI. And I think that's, this investment in theory is part of the reason why, you see, I would say, especially in the United States, where, you have these billionaires like Jim Simons coming in and really putting a lot of money into theory. It's because I think that they know that they can really make a difference. So yeah, I agree with what Yashar said.
I think, we'll both accept your checks.
Okay, we will get at the last, question. Yeah.
First of all, phenomenal talk, phenomenal discussion. In both of you, with the encouragement of the TSI, come back a year from now, because computational speed is picking up and there's more of it, but how it goes every 2 years. You are going to know so much more, and you're going to communicate it next year or 2 years from now at the next month. So, come back again.
It's a pleasure. I think next year is going to be a GPT version of us.
Yeah, I would add to that sentiment that literally yesterday, I learned about the discovery of the faintest galaxy ever discovered. I think it's called Unions 1. We heard about it in yesterday's TSI seminar. And this is a galaxy that only has a luminosity, I think if memory serves, 16 solar luminosity. So it's like having the equivalent of 16 suns inside of just this galaxy. So very faint, so overwhelmingly dominated by dark matter. was having discussions with the person who just, his group discovered this about all the implications, again, things that he hadn't thought of new ways that his observation could be used to test theory of dark matter. So it is a very active thing. And again, it's like when you put people in the same room and maybe give them some caffeine, a lot can happen. So yeah, absolutely. I think you're spot on with that question.
So we are gonna end the panel discussion. I wanted to thank again the two speakers. This has been an amazing panel discussion. I'm in condensed matter physics, so I'm not an astrophysicist, but I really enjoyed it, and I'm very thankful that you did like such an engaging and talk for a general audience. This was really great. And I also want to thank the audience for being so engaging and interested in this. It's great to see young and older people all together being very interested about astrophysics. So I'm gonna end. This was part of the public talk series. So every month at McGill we hold these public talks. The next public talk is gonna be on materials in disasters. So what is the role played by materials in disasters such as the Titanic and bridge collapses that happened throughout history. So it's going to happen on November 28th, and it's given by Nicholas Provatas, who is a professor of computational physics here at McGill. And yeah, you can find more info on the TSI website. One last item. So at the beginning of the talk, when you were entering the room, we asked you to fill out a form to enter the raffle to win a TSI map. So the winner is going to be Martin Labertet. I really don't know who you are, but when you go out, you can take the map which is on the table with yours. And thanks again to the speakers.
I was very happy to have something like that.
I really always like your talks, like the analogies of it. What's the name of the triangle?
That's